of Miami, and Professor Abhinaya Sampath from IIT Gandhinagar. Before I invite them onto the stage, let me introduce them to the audience present here. Professor Pranoy Suraneni is Associate Professor at the Department of Civil and Architectural Engineering in the College of Engineering at the University of Miami. He holds a PhD from ZTH Zurich. Professor Suraneni is an expert in the materials science, chemistry, and engineering of cementitious materials. His research strives to develop long-standing concrete with low carbon dioxide emissions through the use of novel waste materials. The other instructor for this tutorial is Professor Abhinaya Sampath. Professor Sampath is Assistant Professor in the Department of Chemical Engineering at IIT Gandhinagar. She holds a PhD from the University of Urbana-Champaign, US. Professor Sampath's research interests include heterogeneous catalysis, Raman spectroscopy, mass spectrometry, in situ and operando spectroscopy, and electrochemistry. I now invite Professor Suraneni and Professor Abhinaya Sampath later for the tutorial titled Characterization of Nanomaterials. Professor Suraneni.
Okay, thank you very much. Can I have the slide advancer? Okay, fantastic. So yeah, I mean, you guys have eaten lunch. I'm sure you absolutely want to listen to me talk about measurement methods, etc. I'll try to talk for 1.5 hours on this. No, I'm just kidding. I'll try to be short. I'll also try to make this a little interactive so that, you know, I don't have everyone sleeping in every row. So, okay, let's talk about measurement just a little. So, what I did in this, and I'm happy to provide you a copy of this PDF, is I put together a bunch of hyperlinks. So you can, you know, I'm happy to share this with you later, but you can go through the hyperlinks. They present very interesting information, Wikipedia, papers, books, etc. So go through them if you're interested. So metrology is the science or study of measurement, as opposed to meteorology, weather, okay? Nanomaterials, it would be nanometrology, so study or science of the measurement of the nanoscale. So why do we measure is something that we always want to ask ourselves, and I will ask you that. So generally, when you're running measurements, there are a lot of things to keep in mind, right? If you've learned a technique for the first time, and you're going to use it on a specimen that you have synthesized and no one has synthesized ever, how do you know that your measurement is accurate? So this is where things like standards, calibration, all of these come in, right? So you bought a new equipment, fancy equipment, fantastic, spent 20 lakhs or 20 crores or whatever on it, right? But if you're running particles which no one else has run on them, you have no way of knowing that your results are accurate. But if you run a particle that has been run the world over with results that are expected, then you know that you're doing the right thing. So that's where standards and calibration comes in handy. Sample preparation is extremely important. So when you're running something, as an example, you're testing a material in electron microscopy. If you don't do sample preparation properly, you can get artifacts, you can get wrong measurements. So this is something that's very important. This is why in our publications, we write and we go through significant detail explaining the sample preparation process. So you have to do that right. And there are lots of published articles on how to do sample preparation right. Now, at the same time, repeats. So, all of us want to finish our PhDs soon. So we hate having to run a sample 3 times, 5 times, 10 times, 12 times. But there's an old German saying which goes, eine Messung ist keine Messung, which means, oh yeah, no, I'll be careful, I think. So it basically means one measurement is no measurement. So run repeats, know the reproducibility, know what sort of errors you're getting. And if possible, run multiple different test methods. So there's a, it's not a saying, but trust but verify, which is used for a lot of other applications as well. So when you get some results, it's always good to think, yeah, these make sense. But at the same time, you want to run some other tests or you want to compare to literature to be sure that what you're doing is the right thing. All right, why do we need to measure? Someone at the back, this is not a quiz, but why do we need to measure? Someone tell me. Come on, say it. I mean, if it's only me speaking, it gets very boring. Shout it out, it's okay. Why do we need to measure? Yeah, just tell you, no need to raise your hands. To make calculations, to see how something fits in with your theory. Someone else, why do we need to measure? For quantitative estimations, fantastic. We talked about synthesis earlier. Well, you're trying to synthesize something specific. How do you know what you've gotten if you don't measure, right? We talked about transformations earlier. To understand if the transformations are successful, we need measurements. So for any process that you do, to understand whether you've synthesized or whether you have impurities, for all of that, measurement is critical. Let's talk a little bit about powder measurement. What are we measuring, or what are the parameters of interest to measure? So we've seen some pictures like this before. These are various nanoparticles, nanomaterials, etc. In physical terms, we can measure size, we can make measurements of shape, we can make measurements of surface properties, of surface area, and of dispersion. In terms of chemical measurements, which will be covered in the second part of this tutorial, we can study, or we can look at bulk properties, we can look at specific crystallinity, we can look at the phases that form in these materials. For all of these, there are many different tests that you can run, and learning how to run some of these tests is actually closer to an art, right? In the sense that every lab comes up with its own SOPs, every lab comes up with its own methods on how to do these measurements. So again, I've put a lot of links, you can go through them later, and they have interesting papers on how to do some of these measurements as an example. So I'll focus on particle size, shape, specific surface area for the most part. Size, right? So particle size, it seems pretty obvious, it seems pretty simple, right? This is a small particle, this is a big particle. Inherently, it's obvious to all of us that compared to a small grain of rice, a cricket ball is bigger and a basketball is much bigger. But we need a little bit better units, right? If you write in your paper that, let's use a banana. So there was this joke about using bananas for measurement. So if you look at the picture here, right, it says anything can be measured in the number of bananas, right? So, a fish can be 2.5 bananas, a child can be 7 bananas. But at the same time, if you're using it for, selling a product or for science or for lawsuits, maybe you don't use bananas, right? But maybe, you can do very simple back of the envelope calculation and estimate a nanoparticle, how many bananas is it? So typically, size is simple in the sense that it's a measure of how big a particle is, some dimensions of these particles. But at the same time, size and a lot of other measurements are actually very complicated, and the value that you get can actually depend on how you run the measurement itself. If you're interested in some measurement paradoxes, etc., you can look up coastline paradox, which kind of tells you that depending on how you measure the value, you can get very different values of the coastlines of various countries. And that's because of fractal dimensions, things like that. So nanoparticles are small. So your standard measurement techniques, as examples, optical microscopy may not work. But it was pointed out earlier, maybe it does work. Measurement is complex because we don't have just spherical particles. If everything was spherical, it would be very straightforward. But even if things were spherical, I think you can appreciate that this case, which is just one big spherical particle versus a smaller spherical particle versus a collection of different spherical particles of different size, right? Measurement of each of these has its intricacies versus something like this, which is a little bit, it's kind of spherical, but it's not really, right? There's a cloud shape there. So particles, of course, don't have to be spherical. We generally, though, report many things in the form of diameter because it just becomes very easy. So in this case, particle size would just be, this dimension, although you can report multiple different dimensions, you can report averages, etc. The other metric of interest is what is known as dispersity, right? And here it refers to the range of particle sizes that we get. So commonly, if the particles are not spherical, we report equivalent spherical diameter. In this case, it's completely okay. But when you have a graphene, for example, or a very long nanorod, reporting a diameter may be a little inaccurate. So going back to our bananas example, maybe this is 1 banana, this is 0.5 banana. This reported as a sphere is 0.8 bananas. And this has a distribution where there's a lot of 0.3 bananas and a little bit of 0.5 and 0.1 bananas. So this shows the result of a particle size distribution measurement. And you see, right, that there's a complicated distribution. Real particles or real materials often look like this, where here you see this sort of a normal distribution. And actually, after we ground this using a very specific tool known as mechanochemical activation, we created a lot of sub-micron particles, but we also created a lot of 100+ micron particles. So in this case, the distribution is quite complex. You can't just say, hey, the size is X. But of course, what you could say is that the median size or the mean size is X and Y. And you can come up with descriptors, right? You can say 10% of the particles are below a certain size, 90% of particles are below a certain size, 50% of particles are below a certain size. And actually, that's very commonly done in laser diffraction measurements. So, I was really thinking today that I should probably change a lot of my slides because essentially a lot of what I was talking about was already kind of covered, but I got lazy, so it's okay. So nanomaterials and nanoparticles. So as was mentioned earlier, typically the definition is that measurement of less than 100 nanometers in at least one external dimension qualifies something to be nano. But you have 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional. So, and this is one way of classification. There are many others, of course, but if all of the dimensions are in the nano range, then that would be 0D, a nanoparticle, for example. And then as you go up, right, you get various scales. So this would be a nanoparticle, this would be a nanowire or a nanorod, where one dimension is outside the nanoparticle or nanometer range. And then here you have these sheets or coatings where you have 2 dimensions outside that range. And this, I'm using my PDF because the PPT looks bad, but I mean, I was going to turn that around and all that. But that is bulk where nothing is in the nanoparticle range. So this is a very famous saying, God made the bulk, surfaces were invented by the devil. And the reason for that is all of the magic happens at surfaces. So if you believe that the surface area is not important, if you believe that the bulk is just as important as the surface, here's a very simple experiment for you. Take this glass of water and take this glass of water and just pour it and see how fast either of them evaporate. You can pretty easily figure out that when you pour the water out, the surface area is way higher and the evaporation is going to be way faster. Obviously, all chemical reactions, a whole lot of other processes are controlled by surface, not by the bulk, right? So the surface is important. And nanoparticles are especially interesting because, and some of the experts in the room might get upset at what I say, they are all surface. Okay, I mean they are not, but really, they have massive amount of surface, and they have very different properties from what happens at the bulk, which makes them useful for a range of applications. Shape. Does shape matter? Can someone tell me what difference does it make if a particle is round? Or if a particle is very long, who cares? It's about the same size, right? Can someone tell me why the shape of the particle would matter? For any application, really. Packing, fantastic. Different shape particles pack very differently. Yes? Sorry? Cellular uptake. Or even very simple, right? I mean, if you want particles to all flow through something or flow through a sieve or something, if they're long and thin, they'll flow down, but if they're circular, maybe they won't fit through this hole, right? So all sorts of applications, the shape matters, and there are some descriptors for shape. So one of the most obvious descriptors is sphericity. That just tells you how much of a sphere is your particle, right? So this is a particle which is very sphere-like. This is a particle, all of these are particles which are very sphere-like. On the other hand, these particles are really not very sphere-like, right? Because they're very elongated, right? So what you do is basically you compute the ratio of the surface area of your sphere, which has the same volume as the object, right? And the ratio of that and the object surface area becomes the sphericity. So a lot of these dimensionless ratios tell you about shape, okay? So now you have these set of electron microscopy images. How does someone find out what the sphericity of these particles is? So 5 or 10 years ago, what I would do is I would take all these particles, draw them, and then find the sphere, and then I would kind, the sphericity. I'm kidding, no one does that, right? What you would do is you would put this in a software, and it's going to do exactly that, right? It's going to automate that process. So a common way of finding out sphericity, for example, is to image the particles, and then to do image analysis to find out all these various parameters. So there is a two-dimensional variation as well, which is roundness, and you have various parameters that describe how rounded various particles are. So there is also convexity. There is also aspect ratio. Aspect ratio is very simple to explain. If you are very tall and thin, then you have a very high aspect ratio. If you are not that tall and a little fat, then you have a small aspect ratio. So something which looks very blocky, right? That has a low aspect ratio. Something that's very, very long and slender, like nano rod, for example. Something like this has high aspect ratio. Something like this has very low aspect ratio. Again, the particle shape matters. You get these metrics because, when you're doing design or when you're doing synthesis, you're doing it with a certain specific objective in mind, what sort of nanoparticles you want to make. Or, for example, you're trying to take a round nanoparticle and you're trying to increase the surface greatly by creating ridges or textures or something like that. For all of that, we need to understand these. The next parameter is convexity. So that describes the surface properties. Basically, it's telling you some information about the edge roughness. So you put a convex shell, which is best described through a wrap that is tightly wrapped around the particle. So a smooth particle, right, which has, all concavities filled has high convexity near 1. Whereas if you have a lot of texture, a lot of roughness, etc., you would have a low value. And we talked about why shape matters. Why would roughness matter? How do I care if something is very rough versus something is very smooth? Surely that doesn't matter, right? Can someone tell me why roughness would matter? Yes. Sorry? Adhesion or friction or anything like that, right? If you want to look at bonding, right, something that is rough is going to have a way better bond than something that is smooth. So all of these are dimensionless ratios. So in all of these images, for example, you can do some pretty basic image analysis, and that tells you all these parameters. But again, what I want to stress on is the importance of trust but verify. Meaning, it's very easy to run a software and it says, it just gives you some value, right? But then you want to think about it. Do these values actually make sense? So that's one of the things that I want to encourage you, right? Think critically about the values that you get. Do they make sense? Don't blindly trust measurements, because the problem with doing that is you don't know the background. You don't know the theory of that software, right? And maybe you press the wrong button and, these have serious consequences. You don't want to publish nonsense. You don't want to publish results that don't make sense. So always, check, look, see if it makes sense, even if a software is telling you this is what the case is. Surface area, or specific surface area, as some others call it. So this is basically the surface area per unit mass. And of course, as we pointed out, nanoparticles have extremely high specific surface area, sometimes exceeding 100 meters square per gram or something like that. And as the particle size increases, the surface area reduces. So we've already talked about why the surface area is important. And you can actually estimate it from size measurements. There are some very clear and obvious formulae to link size and surface area. So, question. I made 5 different nanoparticles, and for all of them, unfortunately, I don't have the equipment to measure specific surface area. So I measured the particle size for all of them, and I tried to estimate the specific surface area based on that. Fantastic. But then one of the people in my department who didn't like me, all right, so this happens all the time. But anyway, he ran a measurement of specific surface area, and found that for one particle, the specific surface area that he measured was completely different from the specific surface area that I estimated. Why would there be such a huge difference between an estimated specific surface area from particle size and actually measured specific surface area? Can someone, say what they think? Sorry? Roughness would be an obvious thing, right? Because if a particle is extremely rough, then it has very, very high surface, but your measurements do not necessarily capture that. We'll talk about that. What else could be there? Porosity. What else could be there? No, but that's not the only thing. What else could be there? There's at least several other assumptions, right? As an example, when you do all these sizing measurements, they almost always assume that the particles are spherical, okay? So if your 4 particles were spherical, but the other particle was extremely long and narrow, obviously the specific surface area would not match whatsoever. But also, have you considered the possibility that the other guy did the measurement wrong, right? It's entirely possible. Why do you have to trust what the other guy measured, right? So there can be any number of possibilities when you get disagreements during measurements, etc. And this is why, you would always try to say, is mine backed up by theory? Is his backed up by theory, right? If I do some modeling, how does that look like? If, I found a correlation, who cares? If there wasn't any physical meaning behind that correlation, what I had was not particularly useful. My friend or my enemy, showed that I was wrong, but if it didn't have any value to start with, did it really matter in the first place, right? So your correlations are great, but try to explain them. When you get these measurements, you have to have some physical meaning behind what you're seeing. So anyway, nanoparticles obviously have extremely high specific surface area. You can estimate them from size, but remember the assumptions behind both of these methods. Dispersion. So actually somebody pointed out, or somebody was asking the difference between agglomerates and aggregates. And there are many ways of defining this, but at least one classical definition is basically that an agglomerate is typically understood to be somewhat reversible, somewhat physical, somewhat weakly bound, either because of van der Waals forces or something else. Whereas an aggregate is actually bonded or fused particles because of sintering or something else, right? So an aggregate means you can't easily get it apart, while an agglomerate means you can easily get it apart, however you define easily, right? So dispersion just basically means how clumped these particles electron microscopy, for example, then you may be able to see the nature of this agglomerate. If you start dispersing things using a little bit of energy, you may see that it was actually just an agglomerate. Okay, so I will be the first person to confess that I don't know how all of these different methods work, okay? So if you ask me some complicated questions about some of these techniques and I don't know, I'm going to ask Pratim or other people in the audience to answer for me. And maybe they also don't know because there are so many measurements, right? And this is just for physical. Abhinaya is going to talk about chemical measurements as well. So for each of these, I put in a hyperlink. You can kind of go through if this is something that you're interested in. So electron microscopy, DLS, laser diffraction, size exclusion chromatography, BET, laser-induced breakdown spectroscopy, static light scattering, all of these can be used. All of them have different physics, different principles they operate on. All of them have different assumptions, etc. And truly, if you can learn all of these, you would really be an expert in analytical techniques. I'm only going to talk about a few of them. Electron microscopy will be the first one I talk about. Let me check how I'm doing on time. I'm okay, I think. So electron microscopy. How many of you have used SEM or TEM? A good chunk. Fantastic. So this is probably one of the most standard chemistry or material science tools. And think of it like a high-powered or optical microscope on steroids. So essentially, there's two different things that you can do. You're imaging your particles using electrons. And by the way, I'm treating this as I'm simplifying things, so please don't, if you're a real expert on electron microscopy, don't get offended. You can come and tell me afterwards my talk was nonsense. That's okay. So you can use very thin specimens, or you can use thicker specimens. If you use very thin specimens, that becomes TEM, transmission electron microscopy. If you use thicker specimens, that becomes SEM, scanning electron microscopy. These microscopes, essentially, they work on the principle that they take a focused beam of electrons, okay, and the beam is focused using a lot of different, very complicated electronics, and essentially, they hit the sample, okay? If your sample is extremely thin, the beam goes through. If your sample is thicker, then the beam is either, it's going to go back this way, it's going to go back this way, in various ways. And there are devices for focusing the backward beam or to collect the backward beam. So then it hits a detector, and that detector does various things. And you end up with a shadow image of your specimen, or you end up with just the surface characteristics, or in some cases, you end up with something that is reflecting either density or atomic number or something like that. So lots of different types of detectors. And actually, you can get chemical information from this sort of thing as well, not just physical information. So SEM and TEM are only two types. There's also STEM, ESEM, LEAM, all sorts of things. So this is a very nice spider. Has anyone seen a spider like this on campus? No? Yeah, that's probably, so that's been coated in gold, right? Why have we coated it in gold? Sorry? Yeah, so basically a spider is not conductive, generally speaking, maybe, Spider-Man or something, but otherwise spiders are not conductive. So otherwise you basically get accumulation or charging effects. So you have to coat it. I have a stupid question. Gold costs so much. Why are we using gold? Can't we just sell this? Wouldn't I make money? Why not? Sorry? Yeah, so basically the layer is extremely thin, right? I mean, the layer is a nano layer. So you can actually compute the amount of gold that is there on the spider. It's going to be 20 rupees or something. It's nothing. You can take the entire target and it would still not be worth much. So it is coated in gold, right? That doesn't mean anything because the thickness is extremely small, right? You can actually try and measure the thickness, right? Because we are talking about measurement. But the bottom line is that we have to make certain samples conductive. And yeah, this is a TEM, this is an SEM, you put it in. And one big thing is basically that these measurements are typically run in vacuum, okay? It is possible to run it not in vacuum, but that has a whole other level of complexity, which I won't get into. So you get images of particles. You've already seen a lot of images of particles. So if I didn't have any software, I could still estimate the size of this, right? How would I estimate the size of this without using any software? I look at the scale bar. This looks half a scale bar, so 100 nanometers. Is that it? I could do that, but that seems a little imprecise, right? How else would I do that? Yeah, so that's what you actually do. Traditionally, microscopes are all counting methods. So what you would do is you know exactly how long this is, right? So you would draw a line and you would see how many particles you hit. You would draw one more line here, one more line here, one more line here, one more line here, one more line here. And then after drawing 10 lines and counting maybe 70 particles, you get some estimate of the size. So this is why microscopy, etc., are called counting methods. You can do the same with TEM, okay? And similarly, you can also do the same thing with particle shape. Particles roughness, surface, all of those also you can get. But as I mentioned, there are softwares. ImageJ is an example that will give you all of this information anyway. You can also get chemical information. And this is fantastic, right? Because let's say you develop the most complicated process ever. And you made a process where you developed these 8 nanoparticles, let's call them. So all your nanoparticles are in the shape of an 8, where the middle thing here has 5 different elements in different configurations. Well, if you want to find out, is it just the middle thing which has a special composition? You need to have the composition of the top, the bottom, and the middle, right? And also you need to know where the middle is. So for things like this, you need both combined physical and chemical information. And this is when microscopic techniques which have EDX, EDS, etc., come in very, very handy. So you would combine the chemical information with this information. You could create all sorts of spectral, hyperspectral maps, etc., which will tell you exactly where, what is concentrated. Typically speaking, if you want something below 1 nanometer, an SEM doesn't work. If you want something below 0.1, TEM doesn't work. But if you're imaging something, that's about 20 nanometers or something, both SEM or TEM works just fine. And just so you know, yeah, this is about 70, 80 nanometers or something, and this is about 10 nanometers, 15 nanometers or something like that. Sample preparation, incredibly important. Guess what? Your samples can't be wet. The vast majority of biological specimens tend to be wet, right? So you have to have a way of tackling water. You have to coat these samples if they are non-conductive. For TEM, you have to make these specimens incredibly thin, right? And then you have this issue that when you're doing all these things, drying or cutting, etc., are you actually changing the specimen itself, okay? So this becomes very important because if you're changing the specimen itself, great, you measured it, but what you measured is not what you had in the first place, right? So this is again why doing multiple measurements, etc., come in handy. Now, at the same time, what a lot of beginners do, if you're experts, this is boring to you, but what a lot of beginners do is they get one image and then they call it a day. This is a terrible idea because you're looking at really, really very small scales, right? You want to get multiple images. You want to be sure that, if you're looking at a sample that has complexity, you capture the complexity in the set of images that you take. So maybe that complexity is on size or shape, or, maybe 90% of your sample looks a certain way, like this, but 10% of your sample looks like this, okay? If it's only 10% of your sample, you need to take enough images to capture that 10%, right? So this is why getting enough images, things like that, matters quite a bit. Laser diffraction. So laser diffraction is basically a technique in which you hit particles with a laser, and then that laser diffracts. And depending on the size of the particle, the intensity of light scattered, the angles of scattering, etc., change. So you get a particle size distribution as a result from this measurement. So to a certain extent, it's similar to the electron microscopy. However, in the electron microscopy, you have to do a lot of analysis to get that distribution. Here, you get that distribution based on the scattering behavior. So the typical result is some kind of a particle size distribution. And of course, you can actually estimate the specific surface area from a size distribution. However, these sort of measurements always assume that the particles are spherical. You can make corrections if your particles are not spherical, but that means that you need to know what the shape of your particle actually is. This is a very standard test. How many of you have used laser diffraction? Okay, a decent number. So when you're comparing different measurements, right, you need to know what you're measuring, meaning microscopy is count-based, laser diffraction is volume-based. So if you have particles with differential densities, right, then the results may not align. And of course, what this is telling you is an equivalent spherical diameter. It automatically assumes that all particles are spherical. So if you have a set of particles and some of them are less spherical than the others, you miss that complexity in this measurement. You completely miss texture. If you've developed very, very textured particles, the size that you get or the shape that you get from this test is potentially misleading. This is an example, where they used laser diffraction, where most of the sample was fantastic, but then they had this small, impurity or something which turned out to be pretty important, and that was at a larger range, right? So this may not have been caught using some other techniques, but because this technique spans a pretty large detection range, they were able to find it. So the range is typically 10 nanometers to about 1 millimeter, but again, depending on exactly which instrument, which configuration you have, you can go left or right just a little bit. Dynamic light scattering. So DLS is basically you take a particle in solution, and then you hit that with a light. So fluctuations particles in solution are moving basically because of Brownian motion, etc. And essentially what you get is this sort of profile, and the fluctuations in the profile, you can use them and you can convert them towards a size distribution. So here your range is 1 nanometer to 10 micron. So it goes finer than your typical laser diffraction, but not as fine as electron microscopy. but it doesn't go as coarse as laser diffraction. So it's somewhere in between these, as this graph also shows. So depending on the particles that you have, you can choose your appropriate technique. So I asked you before why we run these measurements, right? And we've talked before about aggregation, agglomeration processes. So if you do some sort of aggregation process, you want to kind of know the size of the aggregates, the size of the final particles that you do. So these are the sort of measurements that you would run to confirm whether you've successfully aggregated, fractured, whatever you've done to your materials. Nitrogen adsorption. So it's computed typically using the BET theory. Who knows what BET stands for? Okay, what does it stand for at the back? Brunauer, Emmett, Teller. Does somebody know who Emmett was? Does somebody know who Brunauer was? Do people know who Teller was? Teller is extremely famous, okay? Teller basically, if you've seen the movie Oppenheimer, Teller is there in that. Teller did a whole bunch of good and horrible things with respect to hydrogen bombs, etc. Emmett also worked on a bunch of fission and other related activities. Brunauer is the most interesting guy, at least for me personally speaking. So Brunauer was initially working with Emmett and Teller on these, but during that time, there was a lot of investigation of communism and all that in the United States. So basically, Brunauer got himself blacklisted because at some point many years ago, he had been in support of some communist causes. And in the 1960s, in the US, being seen as a supporter of communism was the end of your career in defense. So Brunauer got kicked out of defense, and nobody would hire him, almost nobody. So Brunauer actually went and worked on cement and concrete, which is what I do. So he worked at the Portland Cement Association for a bunch of while. And the moral of the story is that if no one will take you, you can become a fantastic cement and concrete researcher. So Brunauer, there's actually a very famous award, the Brunauer Award, which is named after Stephen Brunauer. And the best paper published in the American Ceramic Society on cements every year gets that award. So that's my story on BET, which is totally not related to what we are talking about, but maybe you'll remember that the next time somebody asks you who Emmett is. So regardless, so BET is basically a multi-layer adsorption theory. It's an extension of Langmuir and other adsorption theories. The theory you can, at least for me, it's a little complex. I'm not a chemist, but you can kind of work it out. But essentially, it links this adsorption behavior with a specific surface area. So you find out, and you use nitrogen. Can someone tell me why we use nitrogen? Why not use something else? Because it's inert, right? I mean, if this thing is chemically interacting with your surface, what are you going to measure? You've modified your surface. So you use typically inert things. Nitrogen is one, but it can also be various other things, argon, etc. And because we use nitrogen, of course, there's a lot of sample preparation. This has to be done at low temperature. We have to clean the sample. We have to dry it. All of that sample preparation can be quite complex. So we get the specific surface area in meters square per gram. And we've already discussed when and, if it does not agree with other measurements. As an example, electron microscopy measurements or laser diffraction measurement, what this tells you about particle shape, size, texture, etc. Multiple methods. So it's important to run multiple methods. Each of these methods is telling you something, and if you put all of them together, the sum is better than the parts, assuming you've used these methods appropriately. Each method has its own assumptions, advantages, and disadvantages. And if you're really, caring about measurement, you will know to a certain extent, at least, what these advantages, disadvantages, assumptions are. So you can use these methods appropriately. So I say run the most appropriate method, but because we're at the cutting edge of science, sometimes it's not obvious what the most appropriate method is. So if possible, always measure everything, right? Run multiple measurements, trust, but verify, things like that. But also, I mean, we're only talking about experiments or characterization is not enough, right? You can run all the characterization techniques that you want, but sometimes it's not enough to understand, what is happening unless you understand the context of your synthesis, unless you run modeling. A lot of times, I mean, measurements are not good enough for what is happening at the interface, for example, of a 5 nanometer particle, right? This is when you start to use all of your modeling approaches as an example. So with that, I'd like to conclude my talk. Basically, I'm going to repeat the same thing over and over again, but there's a lot of different methods that exist for characterization. Hopefully you get to use a whole bunch of them. You can use physical, chemical characterization techniques. I talk largely about shape, size, surface area. Use multiple methods if possible. And the most important thing that I'd like to leave you, especially the younger folks in the audience, is think critically about what you've done. Think critically, if the values that you got are right, and always try to back them up, right? Nothing exists in a vacuum, right? Your research is built on what others have done, and others will build on your research. So try to reference it back to theory, to papers, things like that. So thank you very much. I think 31, but I'm not sure. Shit.
So hello everyone, I am Abhinaya Sampath. I'm an assistant professor in the Department of Chemical Engineering at IIT Gandhinagar. I majorly work on heterogeneous catalysis. So this is kind of my bread and butter, whatever we do every day in lab, me and my group. Like Pranay rightly mentioned, there is no dearth of characterization techniques that you can have for nanomaterials or for any material in general. So just like how you can use 100 different keywords to describe the character of a person, there are so many different aspects of nanomaterials that you can use to describe the nanomaterial. So in addition to the particle size, shape, and dispersion, I'm going to just touch base on a few techniques which will be telling about other aspects of nanomaterials. So this is something that Pranay talked about. So I will be covering the next 3 points. Starting off with the crystallographic information about the nanomaterial and the composition of the nanomaterials. Many times you don't just have one particular element present in a nanomaterial. It will be a combination of multiple different elements. So how do we know the exact amount of each element that is present in the material? So that one. Finally, we'll close off with how to know the electronic nature of these elements that are present in a bulk material. So can someone tell me, why should we know the crystallographic nature of the material? Where is it important? Any answers? I know you would have all come across the different applications. Right? It has been discussed since morning. Just shout out. Sorry? Catalysis, yeah. So because I work on catalysis, it's very important for catalysis. So let me start off with one application, that is energy storage batteries. Okay. So in this particular work, what they took was graphite and they put the element nickel on it. And they did some treatment of the nickel to get the activated graphite, which contains nickel on the surface of the graphite. And they used CVD. What is CVD? Chemical vapor deposition. And they deposited, A here stands for amorphous silicon on the surface. So what they observed was, when you put the amorphous silicon, it helps really the lithium ion transfer in the lithium ion batteries. So this was a very good anode material they found out. So this is only one of the million applications where the crystallographic nature of the material is going to determine the performance. So what is amorphous? So, so amorphous and crystalline, so they are like a way to characterize the materials. That is, when you have long range order, the order in which the atoms or molecules are structured in a particular material, you call it crystalline. If not, you call it amorphous. So how do you know in this particular paper, let's say they made this material, they called it amorphous silica being deposited on the material. You think people will believe it? They're not going to believe it, right? Unless you provide proof of it. So along with the invention of newer and newer types of nanomaterials, people are also working on characterization of this nanomaterial. So this is a big field in itself. Like, how do we develop methods to prove that whatever we prepared is actually what we prepared? So the first technique that I'm going to talk about is the X-ray diffraction. So this will tell us more information about the kind of crystallinity that we have in the material. So how it works is that you take any bulk material, crystalline or amorphous, you put some X-ray beams on the surface at a particular angle, particular angle theta. And the wavelength of this X-ray is it's told by the lambda. So what will happen is, this particular material is going to scatter your incident X-rays. And they are going to go in all possible directions, because scattering can happen in any possible direction. And when the scattering of the X-ray happens, there are two things. One is called the constructive interference. Another one is the counterpart destructive. Okay. So when you have a material, when multiple scattered beams are there, destructive interference happens, and then you lose all of the scattered beams. But when you have this crystalline material, what will happen is that the order of the material will scatter the beam at the same angle theta, that is the angle of incidence of the X-rays. And all these constructed scattered beams, constructively interfered scattered beams, are detected by some kind of detector that you have in the system. And the relationship between the angle of scattering, the incident wavelength, is related to the interplanar distance in the crystalline material by this particular equation. So this equation is called the Bragg's law. So this is named after the people who came up with this equation and also awarded the Nobel Prize for it. So when you do this experiment, the machine is basically telling you, when you have the lambda, this is the angle at which you are collecting the scattered beam. And as you keep changing the theta, you will get different information about different kinds of interplanar distances that you have in the system. And these interplanar distances are kind of the fingerprint of the material or the crystals, the kind of crystals that you have. And hence, you will get a data which looks like this. This is basically telling you intensity or the relative amount of each type of crystal that you have in the material as a function of the angle of incidence. Now, what are the advantages of this method? I am sure all of you would have seen an X-ray machine used in a hospital, right? Does it operate at ambient pressure? Yes, you don't really have any special requirements with respect to where you put the X-ray machine, right? Similarly, this particular technique, which only uses in X-rays for the incidence and also just collects the scattered beam, which are X-rays again, this method can be done under ambient conditions. We will see why it is very important when we talk about the other techniques. And also, this particular technique is going to tell you information about what all elements are also present, not just the crystal information, but also the elemental composition can also be found out using this technique. But the disadvantage is that you will only know information about whatever crystals are there in your sample, but you will not know anything about the amorphous phases, because your amorphous phase is not going to scatter the beam in a particular way for it to constructively interpret. So whenever you have a sample, you get some peaks. All you can say is this particular crystallographic plane is in your sample, but you cannot say anything about the amorphous substrate. Now here are some references. So always, for most of these characterization techniques, you can start off with Wikipedia, and then you can follow the references given in the Wikipedia or some other books provided in this presentation. Hopefully it will be given to you later. Now, let's say I do the XRD of a particular material, and then I get this particular plot. So here, the sample that was taken was the cadmium and the sulfur crystal. So if you look at the cartoon of this particular material, there are different possible crystal planes that are present. And the interplanar distance between different kinds of crystal planes are going to be different. So based on that, you are going to get the scattered beam at different theta. That is the angle of incidence. Now, with just this information, let's say you do not know anything about what is 100, 002 and all that. Can you easily identify the crystal planes? Or how do people come up with these indices? So there are a lot of people who do computation. Okay, so they do computation, they take pure crystals. If they're arranged in a particular way, what is the angle of incidence at which you are going to get the scattered beam? So they find out. And there are also experimentalists who prepare pure crystals and then they do the XRD, they take that as the reference. So for analyzing the data that you get during the XRD measurements, you really need reference images or some reference data which are easily available online. And most of these equipment come with sophisticated softwares which are inbuilt with this database. So as and when people find out new information about new types of crystals, it is published and then incorporated into these sophisticated softwares, which in turn process the data and tell you what are the crystal planes that are present in your surface. So now, moving on to the second part. What is the actual composition of the materials? Let's say you have the same cadmium sulfur. Okay, the relative amount of the cadmium and the sulfur is going to decide what kind of structure the material has. Correct? So when you have, say, sodium chloride, you have to have Na and Cl in stoichiometric ratio, right, in order for it to form NaCl. Similarly with many other types of crystals or any other material. So the composition of the material is going to determine a lot of properties of the material itself. So what are some of the techniques that people typically use to find out the composition? So I'm going back to the same example. So we talked about like the importance of having amorphous or crystalline material. When you take this example of having the nickel in the anode, the amount of nickel or the amount of silica or amount of graphite is going to really determine the performance of the battery again. So that's why it is important. So whenever we do a liquid phase chemical synthesis, it is almost like being in a classroom. Okay. Most of the time students think they have imbibed everything that the instructor has said. It's only when you take the test, you know what is the percentage of retention you have. The characterization is something similar. So whenever you have this liquid phase synthesis technique, you think 100 is ending up as a solid substrate, but that will not be the case. It will mostly be 80%, 70%, sometimes even 10 or 20%. So that is why it is important to know once you make the material, what is the actual amount of material that is going into your sample. So the first technique which people widely use is called the ICP-MS. The ICP-MS stands for inductively coupled plasma and MS stands for mass spectrometry. So what happens is that you take any liquid or solid sample, you digest it using various reagents, especially using strong acids like nitric acid, as shown here, and then you prepare some sort of a solution. And this solution is atomized and then subjected to a plasma treatment to ionize. So basically, let's say your sample has 3 different types of elements. So these 3 elements are ionized using plasma. And once you create the ions, you subject it into a magnetic field. So when you know that when ions move in a magnetic field, the velocity or the trajectory is going to be determined by the mass and the charge of these ions, right? So based on the mass of different elements, their trajectory is going to be different. So they are kind of separated from each other. And once this separation happens, you have a detector which basically detects the concentration of each ion that is coming to it and thereby gives you information about the mass to charge ratio and the respective concentration of the ions. So this is how this ICP-MS works. The advantage is that you can even get concentrations in the ppb, that is parts per billion amounts, parts per million, parts per billion. And it is relatively fast, but the disadvantage is that you're going to destroy your sample, because remember, whatever sample it is, you have to digest it, you have to ionize it, and then you have to detect it using a detector. So you lose your sample. And you also have an elaborate sample procedure. We know that whenever there is a synthesis technique that involves 10 different steps, it is like the number of steps is proportional to the number of mistakes that you make, right, in the lab. It's always the case. So there are a number of steps here. That means the more the number of mistakes that you will be making. So what can be the alternative to this? So there comes EDXRF, and the full form is Energy Dispersive X-ray Fluorescence Spectroscopy. So this is something that is close enough to the X-ray diffraction that we discussed. In a way, what happens is that you have a sample. There is no need for digestion or any pre-treatment of the sample. You just take your solid sample and then you just put some X-rays on it. So when you put X-ray, the X-ray has enough energy to excite one of the electrons in your inner shell of the elements that are present in your sample. And that electron is ejected out of the system. So the electrons from the outer shell de-excite to fill the hole that is created by the ejected electron. So the difference in the energy is emitted as the secondary X-rays or the fluorescent X-rays. In this technique, what you do is, you know the wavelength of the primary X-ray, you detect the energy of the emitted X-rays, and with this information, you can get details about what is the element that is present. Because we know that the binding energy of these electrons are going to be fingerprint of the element identity. So the advantage is that it is non-destructive. You get your sample back, unlike ICP MS. And then this is non-expensive. You don't need expensive reagents to prepare your sample. But the disadvantage is that, let's say, even dogs are interested in my lecture, looks like. So this is the kind of data that you get from the EDXRF. Okay. Basically, what you get is intensity or the counts on the y-axis, and the x-axis is nothing but the energy of the emitted X-rays. So, so what is happening is that when I have multiple different elements in my sample, depending on the identity of the incident X-ray, I am going to excite different kinds of electrons in my element. And that is going to result in different kinds of fluorescent X-rays that are emitted out of my sample. So these are the kind of peaks that you would get for typically the metals that are present in your sample. And I would like to point out that not all X-rays are able to excite any possible core electron that you would have. You need enough energy in the incident X-rays in order to excite your electrons. So that is why, depending on the identity of the incident X-rays, you have the different kinds of excitations that are happening in the sample, therefore different peaks. Similar to X-ray diffraction, where you need reference, where you need people to do some experiments for you, tell you for a pure crystal, this is the diffraction pattern that you get. Similarly, for EDXRF as well, you need references. So what you do is, you take a mixture of two elements, you do EDXRF, and then you see what is the result that you get. And then you add the third element, and then you do the EDXRF again, and you see what is the count of each element that you get. And whatever the relative changes in the peaks are tells you the composition of each element. So these are the kind of references you have in the EDXRF experiments. And this doesn't really work well with light elements. So these are typically done for heavy metals, like you would see in this particular graph. Now, moving on to the third technique. So Pranoy was mentioning about the use of transmission electron microscope for finding out the size and the shape of nanoparticles, right? So when I have an electron beam that is hitting my sample, there are multiple different things that can happen on my sample. So what can happen is you can create secondary electrons, because when you are ejecting an electron, that can be done using not just an incident X-ray, but also an incident electron beam. And also, when you have the secondary electrons that are being ejected out of the sample, it is also possible for the sample to emit secondary X-rays. It's not just when you put X-rays on the sample that you get X-rays. When you put electron beam on the sample also, you can get X-rays out of it. So when I am doing this electron microscopy, there is one detector that is capable of measuring the excited electrons. What if I have another kind of detector which is basically measuring the emitted X-rays? When I am measuring the emitted X-rays, I will be able to get information about what kind of element that is present. Basically, I'm clubbing the EDXRF with the transmission electron microscopy measure. And then what is the result is that these are two images. This is a mixture of iron and manganese that is present as a spherical particle and also a rod, and images that you would get when you're basically measuring the electrons that are ejected from your sample or transmitted through your sample. And when I start measuring the X-rays that are emitted from my sample, by using the energy of the emitted X-rays, I can say where iron is present and where manganese is present. And I can put these two mapping on top of each other, and I can get information about where exactly manganese and iron are present when there is a compound of manganese and iron. So this is for the spherical particle and this is for the nanorod. So with the same equipment, there is a possibility of getting various different types of information: shape, size, and elemental composition as well. So this is one of the most sophisticated techniques people use these days to do multiple different information about the nanomaterial. And the advantage is that, of course, the nanoscale imaging. You can measure samples as low as 1 nanometer in length or in any particular dimension. And you also get the elemental mapping 2 and 1. But the disadvantage is that sample preparation is extremely hard for these kind of measurements. Most of the time, a research student enters the lab, is very enthusiastic about getting colorful images for a manuscript, goes there, gets nothing. So this is the standard story in every lab. At least for the first 2-3 tries, they really get nothing. And after that, they get a hang of the technique and also the sample preparation. So it is extremely hard. And most of the times, you will also see that for XRD, EDXRF, and all those kind of techniques, you would have graduate students handling this equipment. But for missions like TEM or ACM and all, you will have technical assistants who are specializing in these techniques to handle the equipment, because they are really not that straightforward to operate. So now moving on to the final aspect, like the electronic nature of materials. So let's take the same example here. I'm showing you an image. There is manganese, there is iron that is present. Is it possible for me to say this manganese and iron are interacting with each other? Like, these are atomic scale images, right? Like, is it possible for me to say that? They are close to one another, but is it possible for me to say there is some kind of interaction between the two? At least by looking at this image, it's not possible, right? But most of the time, when you have multiple elements present in your sample, you don't want to just know whether they are close enough to each other, but also, are they chemically interacting? In the sense, is there a charge transfer between these two elements? So let's say I have carbon and oxygen on my sample. It's not enough if carbon and oxygen are close to each other, right? I want a bond between the carbon and the oxygen. So if I want to prove that when multiple elements are present in my sample, there is actually an interaction between these elements, then I need to know the electronic nature of the element. That is, how much of charge transfer is happening between 2 elements or 3 elements. So I would like to show this video. So this is one of the places where it is really important to know this particular information.
Is not into wafer in this. Interesting, those raw wafers are 300 millimeters in diameter and less than a millimeter big. In our opinion, 35 glass chips are then made of each exists. In numerous process stages, the wafers are given their characteristic surface structure. After coating with a photoresist layer, the wafer surface is exposed without and etched. This results in the desired conductor structure. Such structures are hundreds of times smaller than a human hair. Dopants are then implanted in the material to increase the electrical connectivity of parts of the semiconductor. In subsequent phases, this and other process steps are repeated until the entire layer of the chip has been deposited on the wafer. This results in the wafer to the 100 degrees Celsius. In some cases, up to 27 times. Up to 200 measurements done, and up to 26 exposures. All in all, this can be as many as 700 process steps and 14 weeks process time. Once this is completed, the microchip is assembled in as many as 30 such layers, like a mini skyscraper. Each layer has its own function. Interconnecting them makes the microchip highly complex. Semiconductor chips, the building blocks of our future.
So the semiconductor business, something you cannot really avoid in today's scenario, right? Everybody is talking about semiconductor boom in India, abroad, everywhere. So in addition to the interaction between different elements that might be present in the bulk, sometimes it's really, really important to know what is happening at the surface. And sometimes, or many times, in these kind of sophisticated applications such as semiconductor industry, the surface would be very, very different when compared to the bulk. So you need techniques which will be selectively telling you about the surface versus the bulk. The X-ray photoelectron spectroscopy is one such technique. Here again, you take your sample, a solid sample. It could be a thin film, it could be a solid material, it could be a crystal, anything of that sort. You put an incident X-ray on the sample, and when you put the X-ray, you know it is possible to actually excite one of the core electron of this material. And this ejected electron is called the photoelectron. And the kinetic energy of this photoelectron is it's going to be, so the kinetic energy of the photoelectron plus the binding energy and the work function, that is the difference between the conduction band and the valence band energy, is going to be the h nu, that is the energy of the incident X-ray. So this is a simple formula of energy balance. So in this particular technique, you basically measure the kinetic energy of this photoelectron that is ejected. You know what is the incident X-ray energy, and thereby you find out what is the binding energy of the electron. And this binding energy of the electron is going to be again a fingerprint of the element identity. And therefore you know what are the elements that are present in your sample. Now I told you two things. First, I said this is very surface sensitive, right? How is this surface sensitive? Because this is something that is happening also in your EDXRF, right? When you have the energy dispersive X-ray fluorescence, you are putting X-ray on the surface, there is an ejected electron, and there is secondary X-ray emission which you are measuring. How is this different from that? So the differences is mainly coming from what you are measuring. In the EDXRF, you are measuring the secondary X-rays that are emitted. But here, what you are really measuring is the kinetic energy of the electrons. Okay? So if I have electron under ambient conditions when there is air around, what would happen? What is the lifespan of an electron, free electron? Is it going to travel several layers? Let's say I have several layers of my bulk material. Is it going to travel through it? It's not possible for the electrons to travel through it, right? So this particular technique, that's why it is very surface sensitive. So whatever electrons that you're ejecting from the surface of your sample is what is going to be measured by your detector. Therefore, it is going to tell you what is happening at the surface level and the surface composition. And the second point is, unlike my other X-ray measurements, that is EDXRF or X-ray diffraction, I need to perform this under vacuum. As you can understand, the electrons are not going to have a longer lifetime when you have the ambient air around. Okay. So I'm really simplifying things here. It is possible for you to do XPS under ambient pressures these days. People are modifying this technique. But I'm talking about one of the a primitive XPS, you can say. So this is a working principle of XPS, and the advantage is that it is quite accurate. It is going to tell you surface versus bulk composition. And the disadvantage is that it is going to be very, very expensive. Whenever you need to create a vacuum, you're going to increase the cost of the equipment because you're putting in additional things like pumps and all that to maintain that particular vacuum. So it is quite expensive, and it might also be destructive when you're putting the sample and then you are ejecting electrons out of it. It is going to be destructive for many samples, depending on the conductive nature of the sample. And sometimes the sample preparation also can be difficult for this, but it is not as difficult when compared to, say, your TEM. So, okay, so this is the kind of graph that you get. Let's say you have a mixture of chromium, carbon, and aluminum, oxygen, all of it on the surface of your sample. It is going to tell you basically the intensity of some photoelectron that it is measuring as a function of the binding energy of each of the photoelectron that is being emitted from your sample. And this binding energy, you know, it is going to be a characteristic of the element that is present on the surface of the sample. And people have done a lot of studies with pure elements again, and then created a database for these elements, like which element will have what kind of binding energy and what kind of excitation. And you can always compare the data that you obtain from XPS with these reference measurements and then get an idea of what kind of elements you have on the surface. So coming to the first question I asked, let's say I have silicon, oxygen, and a nitrogen on the surface of my sample. With the help of, say, my EDXRF or the EDX along with the TEM measurements, I would be able to tell whether my silicon, oxygen, and nitrogen are close to one another. But will I be able to say whether there is a bond between the silicon atom and nitrogen? So for that, here is the data. They put just the silicon dioxide in XPS and got this particular peak, which is talking about the binding energy of the electron in the 2p orbital of the silicon. Now, when they mix or successfully dope the nitrogen and then form this particular compound, they take this and do the XPS on this particular sample again, and they're able to see the shift in the binding energy of the electron from the same 2p orbital of the silicon. So this is because there is a charge transfer between the silicon and nitrogen, and because of which the binding energy of the core electrons are going to change. And this change in the binding energy can tell me successfully whether there is a bond between the silicon and nitrogen, which is something that cannot be obtained using your other techniques such as the EDX. So just to summarize, I have only told you or scratched the surface of the techniques. when it comes to getting these different informations. There are so many more techniques, and the techniques that I discuss, they're also discussed in a very, very simplistic way. For example, the TEM, people are doing modifications to it so that they can be done under high pressures or not necessarily under vacuum. Same goes with the XPS. There is something called the ambient pressure XPS. So let's say you want to know what's happening to your sample when there is air around. You cannot be taking it outside of the air, putting it in XPS under vacuum and examining it, right? It's going to behave differently. So people are developing such sophisticated technique, and this development of the sophisticated equipment is an area in itself. And it is allied with the nanomaterials, and it is definitely of interest to many, not just industry people and also academicians. There are people out there who work on this dedicatedly in academic environments also. Okay. And thank you for your attention. I know it was a difficult time post lunch. So happy to take any questions.
Aggregation is there. By which method can be?
So there are many techniques. For example, you can just collect samples at different time intervals and use TEM. And depending on the particle size, you can also go for SEM. Sometimes it is also possible to do UV visible spectroscopy. The absorbance of light by these materials is going to be of the size of the particles. So for example, the gold, it is going to have absorbance at different ranges depending on the size of the gold particle. So that is also another technique.
At a different time.
Yes.
Day 1 or day 0, then
Something.
So if you differentiate aggregation as being something permanent versus agglomeration as being something non-permanent, then you can also try to, disperse it lightly and see if the size persists or if the size changes. So upon putting in small amounts of energy, if there's a size change, right, it indicates that the nature is, temporal rather than permanent. So you can do all sorts of processing techniques and do tests before and after to see if there's any change in shape, size, dimensions, etc.
So we also do in pharmaceuticals. We are doing for zeta sizes, zeta potentials. Check that it is negative minus 40 or plus 40, so that it will not eliminate or become the aggregators. Stability, so to check the stability of the nanoparticles.
Yeah, that is definitely another way to, depending on the context.
Which the nanoparticle is made of.
What do you mean by molecular structure?
So sometimes we synthesize nanoparticles of various drug molecules. So is it a technique which is available to confirm that the particle which is made up of is having the same drug formula or the molecular structure retains even after forming a particle?
I'm definitely not qualified to answer that.
I can answer a little bit. So depending on whether it's, amorphous crystalline XRD could work, right? Some forms of NMR could also work. So there's various different techniques that you're using. If you're interested in the physical ones, largely they don't care if it's organic or inorganic, etc. Obviously, if they're aerosols or polymers, then you have, again, different techniques, etc. So each of these techniques is, some of them are better for organics, some are better for inorganics, things like that. But for your specific application, it sounds, on which I'm also not an expert, but it sounds like NMR or XRD could work.
I would also like to add that for most of these techniques, as I mentioned, you need standards or references. So if you are just developing something for the first time, it might not be possible for you to say, this is what I have prepared using these techniques. So that's when the computations really help. I know a lot of people try to determine the structure of these organometallic complexes and such using computations. So that is something you can think about.
The dean was saying spectroscopy, and indeed FTIR, Raman, and all sorts of other spectroscopy would also work.
I have one question regarding particle size measurement. So we are measuring in the lab by the TEM and DLS, that is okay. But is there any method that we can analyze during the process? Is it achieved online or not? Like if I am doing ball milling, scale down approach, so can I detect is it done online particle size achieved or not without any sampling?
I am not aware, maybe others are, but it also depends on what sort of process you have, right? I mean, if it's it depends on the process. That's a very specific question. Generally, in my expertise, would do it through sampling, right? But maybe somebody else is aware of something like that, how you would do it online, but, sorry? Okay, so there are inline DLS. Okay, there you go. Yeah. Yeah, with sampling, there's a lot of different techniques you can do if you're sampling, but without sampling to do that, yeah.
I would also like to add that TEM generally is done under vacuum, right? Because you have the electron beam that is transmitted through. But now there are techniques to actually increase the pressure and also do TEM under non-vacuum environments. Those are also techniques that are available now. Hopefully soon enough, they should be able to do TEM under ambient conditions so that there will be inline TEM as well, or online TEM.
In situ DLS, I'm not an expert on. In situ XRD only under certain very, very, very specific circumstances would be possible. In situ DLS, I have no expertise. Yeah, mobility techniques would work.
Am I audible?
Yes.
So I would like to determine the average crystalline size with the help of Williamson-Hall method. I might be not aware about this, so can you please give brief some on it?
You mean from the XRD data?
Yes.
There are definitely well documented techniques on how to calculate the crystallite size.
Actually, I have tried to measure and compare with the JCBDS data number, but my plane size would be differ, which is mentioned in the reference. XRD plane.
Okay. So is it possible that your sample is not completely crystalline? So the peak width is going to tell you how crystalline or not so crystalline your material is. So if your peak width is different from whatever the reference that you have, it's possible that your material is more towards amorphous than crystalline. That could be the reason why it's not matching the reference.
Yeah. Maybe you also have some sort of a core shell structure, or maybe there's multiple different materials interacting. Yeah, could.
Scherer equation. Yeah. Yeah.
If it is possible, I will come.
Sure, yeah.
So while setting up the standard or the reference for any experimental technique, what should we consider? Like, should we consider the theories and mathematical calculations, or the various permutation and combination of set of experiments, like for more number of time? Because we don't know the what could be the, because we are setting up the standard, a reference for any sample preparation. So what should we consider? There might be a conflict between the experimentation that we are doing and the mathematical calculations that we have.
So what should we consider at that time while setting up a standard or reference?
So, I mean, let me try and address that, right? Typically, your standards are supposed to be simple, right? So they're also supposed to be well known, well characterized. So for a lot of experiments, when you get the equipment, you get standards along with that, right? Because these are materials, just as an example, in the US, the National Institute of Standards and Technology, NIST, right? They develop standards. So standards are widely accepted. Standards are such that, 1,000 people have measured them. So typically you don't come up with your own standards. You buy standards that everyone else, or you purchase standards or you obtain standards that everyone else is using. These are generally things that have very clearly defined compositions, clearly defined particle sizes. And of course, you can make up your own standards as well. So as an example, just as an example, let's say I'm developing a bunch of materials which have calcium carbonate or something as a composition, right? So it's very easy to get limestone, right? And then some of my standards could just be limestone doped with very pure SiO2. So then I can make up my own, standards, and then I run a bunch of these. And generally speaking, the way you know that your equipment is working okay, etc., is every month or every 2 months or something, you run a standard, you see that everything is okay, right? So standards, calibrations, all of these work in that same way where, you understand these materials, others have run it as well. So one more way in which, you're kind of sure of your measurements is that you run something, and then if you're really wondering what's happening, assuming the test is non-destructive, you send the same material to some other lab and they run it, and then you can compare across labs, etc. Typically, standards are developed through interlaboratory, round-robin testing, things like that.
So basically the combination of experiments that we are doing, number of experiments.
It's not necessarily a combination of experiments, meaning typically standards or reference materials, etc., are equipment specific. They don't have to be, but at least in my experience, they tend to be material specific. But of course, if you have very nice, very pure SiO2 or CO3, they can be used across experiments as well. It's just that, because we have so many different techniques, there's so many different media, etc. Typically, standards don't scale across equipment. It's more, this equipment, this is the standard. By equipment, I mean TEM versus laser diffraction or something, not different TEMs. A standard in principle should work for all different TEMs.
Thank you, Professor Surareni and Professor Sampath, for the tutorial on characterization of nanomaterials. There's an important announcement. Please ensure that the mic is on and you've received the mic in case you're answering the question. This is not for the resource persons or the audience that is asking the question, but it is for the YouTube audience that is watching the streaming of this workshop live at this moment. So have you ever wondered about different computational and theoretical techniques that can study and predict the properties, structures, and behaviors at the nanoscale? If the answer to this question is yes, then the next tutorial is for you. It is titled Modeling and will be conducted by Professor Pratim Biswas and Professor Kaustubh Rani. So it is over to the two tutors for the session now. First of all, it is Professor Rani.
Hello, can you hear me? All right. So welcome back. And what we are going to talk about are modeling of nanoparticles. So the methods that we will see are related to modeling. I mean, I will give examples related to nanoparticles, but many of these methods are also applicable to other nanomaterials, right? Not just nanoparticles. The first important thing that I want to mention here is when I say modeling, always, as was also mentioned during one of the lectures, models are always associated with assumptions, Okay, so whenever you say something is a model, by default there is an assumption associated with it. So keep this in mind. So we are going to divide it into two parts. So the first part I will take, where I will look into the computational methods used to model the nanoparticles at very small scales, atomic scales, and that level. So here we are going to mostly talk about the molecular simulation methods. Okay. The second part will be taken by Professor Pratim Biswas, where he will talk about particle formation, nucleation, and growth collision models, and also other models at a larger scale. So let's first see. Now this is a very popular image. Now why we want to do molecular simulations? How many of you heard this term called molecular simulations? How many of you are familiar? Okay, so you know something like, you may have heard about this term molecular simulation. So for those who are from this field, this particular image is quite popular. Okay, in every presentation, whenever a molecular simulation introduction is given, this slide you will see. Basically, it talks about time scale of the system and versus the length scale. Okay, so if you see at very large time scales and length scales, you have different kinds of models. If you think about thermodynamics, right, which you studied in undergraduate, or even if you think about fluid mechanics, we talk about materials as continuum. We don't think about those materials made up of atoms and molecules. And that works at those large scales, right, because there we can use theories related to the, make this continuum approximation. Then there comes this micro scale, where some aspects of the discrete nature, right, the discrete nature of the material needs to be taken into account. And at even smaller scales, where we are going to look at today, that is the molecular scale, and between molecular scale and micro scale, the discrete nature of the material is very, very important. So you need to take into account the composition of the material, that is they are made up of molecules and atoms. So another important reason why we need to do molecular simulations, right, of nanomaterials is the number of possibilities, right. What I mentioned here as the degrees of freedom. What you see here is a collection of, is a simulation results from a collection of different kinds of nanoparticles, right. Of course, they are model particles containing different shapes. You can see them as different colors, right, prisms of different, pyramids of different colors. Now you can see that the number of arrangements that are possible, right, if you mix them together, are numerous. There are billions of arrangements that are possible. And since there are so many possibilities, it is not possible to come up with an analytical solution, right, to predict the structure of such kind of materials. So you need to do simulation, you need to do numerical calculations in order to predict study this system, because there are several degrees of freedom. Whatever I am going to talk about, the foundation of those methods is a framework called as statistical mechanics, which is actually the is a framework which allows us to compute properties and relate the properties which are calculated using the molecular scale information to the macroscopic properties, right. So statistical mechanics is very important. And those of you who are really interested in studying molecular simulations, it's very important that you study statistical mechanics or statistical physics, because many of the molecular simulation methods that I will talk about, there are software available, and you can actually get results. Even if it comes to something like quantum calculations, you can get results. But in order to interpret those results, and in order to check if those calculations are done perfectly, properly, you need to know statistical mechanics. Okay, so I'm not going to touch upon the basics of statistical mechanics. I'm going to discuss only the methods, right? But keep in mind that statistical mechanics is very important when it comes to understanding molecular simulations. As I said during the previous lecture, all the images, they are I've given the references there, and these references are mostly review articles, and all these slides will be shared with you, and you can refer those references for more information. Okay, so let me talk about the lecture contents. So the way we are going to go is we within the molecular simulation regime, right, we are going to go from very small scale to large scale. So first we are going to look at something called as the density functional theory, which talks about the electronic structure distribution. Then we are going to talk about atomic scale simulations, right, where we are going to see what force fields mean and a basic concept what molecular dynamics is. And finally, we are going to talk about coarse-grained nanoparticles, right, larger scale nanoparticle simulation. So typically, this is applicable to system sizes of very small nanoparticles or even smaller than nanoparticles. This is related to the system size, comparable to 1 or 2 nanoparticles, and these are used to study a collection of nanoparticles, right? Fine. So let me first start with density functional theory. Now, density functional theory, there are several applications. The one set of application is predicting the stable structure. Now, what you are seeing here is a nanoparticle made up of 2 metals, okay, 2 kinds of metals, and one is colored green, other is colored blue. And if you have this nanoparticle, if you want to predict what is the structure that is more stable, whether the core shell kind of structure is more stable or whether genus particle, right, half of it one metal, half of it other metal, that kind of structure is more stable. And in order to do so, you want to know the energies, right? And this is possible using density functional theory. So you can predict what is the most stable structure of the nanoparticle, what is how the spatial distribution of the components is. Then it also allows you to predict the kind of reactions that can happen at the nanoscale. Okay. So here you are seeing this boron nitride nanoparticle, and it is connected to a drug molecule. And this talks about when this dissociation happens, maybe for drug delivery purposes, how this dissociation happens and what are the energy changes involved. Again, DFT is important. So density functional theory is very much relevant if you are trying to study reactions. Another example is catalysis. Again, like this is, by the way, a catalyst nanoparticle, and they are talking about this. This is basically a work from Toyota. So where they are talking about, they are working with these catalytic converters, right? So to remove the NOx. So this talks about like what is the size of the nanoparticle and how its catalytic activity is changes when due to the size of the nanoparticle. Fine. So what is DFT? Very briefly, it is a quantum mechanical approach. It calculates the electronic structure of system. Now, during the previous lectures, at the end we talked about the electronic structure, right? So what this does is, we know that all the molecules, there is an electron cloud around. So it helps us predict what is the distribution of the electrons in the material, right? So the central variable is the electron density, right? And at the base of this density functional theory, there are 2 very important theorems. What is done is, there is something called as Hohenberg-Kohn theorem, or some people also refer to it as Hohenberg-Kohn-Mermin theorem. So there are 2 theorems, theorem 1 and theorem 2. Theorem states that the ground state properties of a system are uniquely determined by its electron density. That's the theorem 1. So if you have the electron density distribution, you can calculate other properties, let's say the total energy of the system and even other properties. So that is one. Second theorem states that the ground state electron density minimizes the energy functional. So you can define energy, right, as a functional of the electron density. How many of you know what functional is? Okay. So to give an example of functional, the simplest functional that you may have seen is an integral. If you know an integral, I is equal to integral of f of x dx, so I is basically a functional of f. So functional is something that depends upon the values of the function over the range of numbers, not just at a single value. So you can define potential energy as a functional of the density. Basically, electron density is a function of the position in space, right? So it's like rho of r. So you can define potential energy as omega as a functional of rho of r, right? So now if you minimize this functional, right, if you minimize this potential energy functional with respect to the electron density, you will get the ground state or the most stable state under those set of conditions. So that's what it means, right? So the basic idea is to estimate using calculations the electron density in space around the atoms using these two theorems. That's it. Now, in order to implement this is in theory, okay, these are the sets of equations, but if you want to calculate it really using computers, to make it practical, what is important is something called as Kohn-Sham formalism. Now, Kohn-Sham formalism is a trick, because if you really want to minimize this functional for real electron density cloud, it is very complicated, right? Because it's a quantum mechanical system, it's very complicated. Because the electrons also interact with each other, right? There is wave particle duality, etc. Now, what Kohn-Sham formalism does, the trick is they map the real system of interacting electrons to a fictitious system of non-interacting electrons. Think of it as an ideal gas of electrons. So if you have a real system, they map it to a fictitious system where electrons are not interacting. Now, when the electrons are not interacting, the formalism becomes simpler, and you can easily minimize this functional to get the electron density, right? Electron density corresponding to the ground state. But that electron density corresponds to the real electron density. That's what the trick is. So, by the way, these guys also won a Nobel Prize for this. So, DFT, two theories. Electron density is central. If you know electron density, you can get other properties. And if you minimize the energy functional, you get the ground state. Second thing is the Kohn-Sham formalism. This is what DFT is all about. Now, whatever the research that is happening in density functional theory, in order to improve it, it is all to do with improving this functional. Okay, the energy functional. People are doing improvements when it comes to having a better functional which is able to estimate properties better. Fine. Very, very computationally expensive technique. Very computationally expensive, and therefore it can't be used for several atoms or big systems. Can be only limited to small systems, tens and even hundreds of atoms if you have a really access to really powerful supercomputers, right? But you can do that only for small atoms, and therefore the examples that I showed earlier, right, they are also small systems, not big systems. So if you want to do it for nanoparticles or nanotechnology, remember it will be for only a part of a nanoparticle, okay, not for the entire nanoparticle, unless your nanoparticle is very, very small. So again, output, what you get? Output, you get the energies. This is what we already saw, right? You can see these different kind of configurations, and from the energy you can predict, okay, which is the most stable configuration, right, when it comes to this nanoparticle to component nanoparticle. You can get the absorption spectra. Yes, you can get the reaction rate. All right. Now, one thing is, you may wonder, okay, I mean, I told you like it is being done for small particles, but in this particular example, again, this is the same paper that I talked about earlier, the Toyota paper. So this nanoparticle looks quite huge, right? How did they perform DFT? So what really they did is, this is the work where they used a combination of density function theory and machine learning approaches. So really speaking, they did the calculations only for this system, and they did it for different configurations, fed it to a machine learning model, and using the machine learning model, they were able to predict for big, large nanoparticles what will be the real reaction rate. So keep in mind that DFT can be used for very small systems, not for the very big nanoparticles. And whenever the reactions are important, DFT can be. Okay. Fine. The next, we go to a slightly higher level. Now imagine that you want to study the nanoparticles, big nanoparticles like this, and you want to study what are the processes, or as I mentioned earlier, the transformations that are occurring in those nanoparticles. Now, if you have these nanoparticles of this size, in order to simulate it, let's say you want to track how the nanoparticle transforms with the time, right? You can't use DFT because it's too computationally expensive, right? Another application is what I also showed in the morning, the nanoparticle going through the cell membrane. Again, for this large system size, density functional theory can't be thought because it's very, very expensive. You can't use it. So in such cases, we use atomic simulation, right? Now we are going up in scale, but also we are going less in rigor. Okay, so we are making more assumptions. So let us see what are the assumptions involved. Now, first things first, in order to do these atomic simulations, we need to know how the atoms and molecules interact. Now, in density functional theory, we used to predict this interaction from very much like fundamental information, right, from the Schrodinger's equations and the density functions. But when it comes to the atomic simulations, we approximate the interactions between the particles, atoms. We approximate them using certain functions. Functions like Lennard-Jones potential, Coulomb potential, Mohs potential. And these functions have parameters. So this is this set of functions and parameters is something that we refer to as the force field. So force fields are nothing but functions giving you the interactions between the atoms or molecules and the parameters for different atoms and molecules. So there are several such force fields for different systems. Now keep in mind that if a force field is generated or developed for a particular system, it is not easily transferable to other systems. For example, if I am using simulating a water molecule to study critical point of water or vapor liquid phase equilibrium of water, I can't use the same water molecule to study the proteins or reactions or other kind of phenomena, because the force fields, keep in mind, they are approximations and they are parameterized for a particular phenomenon, a particular set of properties, and their accuracy depends. Here I have showed you some force fields. For example, charm, amber, OPLS, they are used for biomolecules. Again, there are subtle issues there. There is an embedded atom method which is used for metals, compass which is used for polymers, organic, inorganic. These are some examples. There are several force fields. Every now and then you will see a new force field developed for a particular system. How they are parameterized? They are parameterized using experimental results and a high level theory, that is the DFT calculation. So they parameterize the force fields, they predict those parameters so that they can reproduce certain experimental results or they can reproduce certain density function theory calculations. Clear? So the very common, very popular atomic scale simulation technique that you may have heard about is molecular dynamics, right? As the name suggests, we track the dynamics of molecules. Now, how do we do that? It's same as in case of classical mechanics, right? If you have a system of particles, right, and if you want to study how those particles evolve, positions evolve with time, what you will do is you will solve Newton's equations of motion. It's a multi-body problem, so you won't get an analytical solution, but you have to solve them numerically. So what you will do at each and every time step, you will calculate the force on a molecule or atom from other atoms, and you will predict the position, the next position of the atom, so on and so forth. So you will perform these calculations with time, and that's how this molecular dynamics simulation works. So this is how the workflow exists. Like you define the initial configuration of positions or atoms of the molecule, and also you tell them what are the force fields involved, what are the interaction parameters involved. Then you integrate the equations of motions. I have shown here the Hamilton's equations, two equations of motion. These are nothing but the Hamilton is like the, you can roughly say it's the potential energy with respect to the position, gives you the negative of the derivative of the momentum, and potential energy with respect to momentum gives you the velocity, right? You solve them numerically, and then that's how your system evolves. So if I have a bunch of molecules, with time those system will evolve, and what I will do is, if I want to calculate certain properties, I will take the average of the those properties over the time. I will take the time average, and that's how I get the properties from molecular dynamics simulations. Very popular technique, again very used a lot in industry as well as in academia. Again, keep in mind that though it is less expensive as compared to DFT, so you can use on large number of particles. In fact, now there are molecular dynamic simulations which have been done with millions of particles, millions of atoms on specialized hardware, computer hardware. But still, the computational expenses will scale with the number of particles. Why? Because at each and every time step, you want to calculate the forces or the Hamiltonian. And this calculation is expensive. And this calculation depends upon how many particles you have. More the number of atoms, more the number of calculations you have to do. Roughly, you will say that it scales as n square, but typically in modern algorithms, it scales slower than this, right? Fine. So let's go to, so as I said, the computational expenses scale with the number of particles. So how far we can go? How big system or how big nanoparticles you can simulate in atomistic detail, right? Just to give you an idea, this is an interesting work where they tried to create a configuration, right? Initial configuration as if they wanted to start molecular dynamic simulations of a real cell, right? I know many of our nanoparticles are much smaller than the cells too, but for a real cell, you get an idea that there are 561 million beads, right? Or species they want to perform the MD simulation on. Now this is a, by the way, it's a coarse grain model, so you can multiply it by approximately 4. So that many number of atoms you have in that system. They didn't go ahead with the simulation because it's impractical to do simulations with this kind of system, right? Of course, people may also argue that is there really a use of doing the simulations at this scale using atomistic simulation? But people have done simulations of smaller systems like viruses, right? Which are of the same dimensions at nanometer as many of the nanoparticles that we have been seeing, right? So this is the year-wise, like people have also simulated the SARS-CoV-2 virus, again using specialized hardware. There are computers which have been designed specifically to do this kind of simulation. So what we do, now if we want to go to a larger scale, let's say we are not just, we don't want to limit ourselves to simulating just a single nanoparticle. We want to simulate a collection of the nanoparticles, right? Of course, in order to do that in a practical manner, we have to decrease the number of interaction sites, as I call it, right? So this is what we achieve using the coarse grain. So coarse graining is nothing but you approximate the particles using less number of interaction sites. Got it? As I showed earlier, if you have a nanoparticle, there will be hundreds or thousands of atoms, right? But to simulate, if you want to simulate bunch of nanoparticles, the number of atoms that you need to simulate blows up, right? Like that, and multiplied by the number of atoms in each particle. Now what you do, if you want to simulate those nanoparticles in a very simple way, one thing you can do is you can use simple models where you approximate a nanoparticle as a single interaction site. Instead of simulating it as a bunch of atoms, you simulate it as a single interaction site, and you approximate the interaction between the nanoparticles based upon their chemical nature, based upon their functionalization, etc. So here's few examples are given. Let's say you have a nanoparticle where the ligands are small. You can approximately think of them as hard spheres. On the other hand, let's say you have a nanoparticle which is grafted like this. You can think of it as a hard sphere surrounded by a soft or slightly attractive core. So it looks something like this. Like if you have a hard sphere, the interaction, which is phi of r, where r is the distance between the two particles, it will blow up. This is what hard sphere means. But if you have something like this, you can use something, you can use square well potential, where you have a short attractive well, right? So these are the approximations that can be useful. But here you are only going to take into account the qualitative aspects. This won't be quantitatively correct because you are losing lot of information. This is a very, very, I will say, crude approximation. But the advantage is you can simulate a large number of particles in that way, and you can qualitatively predict interesting phenomena from it. The next is coarse graining, which is more realistic. Now, instead of reducing the entire nanoparticle to a single point, right, what we can do is we can reduce the number of atoms in the nanoparticles to a smaller number, right? So you will bunch the set of atoms in the nanoparticles as a single number so that the number of interaction sites are reduced. So you will create something like pseudo atom. Okay. So this is what it is. Like, let's say your real system is like this. You can, if you have a polymer, instead of simulating all carbon, hydrogen, all the bonds, you will simulate it just like a necklace, like a pearl necklace, right? Sequence of beads. Now, in order to do so, there are multiple different approaches. There is something called as a structure-based approach, and then there is a thermodynamic-based approach. So the structure-based approach uses, does the coarse graining or does this mapping so as to reproduce the structure of the real atomic scale system. When I say structure, if let's say you are thinking of a protein, right? Structure-based approach, what it will try to do is it will try to coarse grain such that it will approximately have the similar structure as the atomic scale protein. Thermodynamic-based approach does it using certain properties. They try to reproduce certain properties like, say, distribution functions, energies, etc., etc. Okay, free energies. So this is an example, right? For example, if you have this unit, you can coarse grain it as a single particle so as to, this is a thermodynamic based approach, so as to reproduce the RDF. So the blue points are the points obtained from the atomic scale simulations, real atomic scale simulations. The red one is obtained from the coarse grain simulation where you reduce this unit into a single particle. This is another example where you see the real atomic had 882 multiplied by 882 interaction particles. You reduced it to a smaller model, 49 by 49, but you parameterize the interaction potential so that it reproduces, right, the atomic scale. So that's how you do it. The advantage, the computational expenses drop down drastically, and since computational expense drop down, you can now study systems which are bigger, right? Okay. Now, when it comes to coarse grain simulations, again there are simulations which are done at larger scale. One important thing is something called as Brownian dynamic simulations. Now, Brownian dynamics, what it does is, what it does is, imagine that you have a nanoparticle of the size of tens of nanometers. Can anybody tell me what is the size, approximate size of the water molecule? Few angstroms. Okay. Now, if you compare the size of a nanoparticle and the water molecule, and if you want to study the bunch of nanoparticles, like this many nanoparticles, let's say, in that case, the number of water molecules that you may have to simulate are in millions. Again, the same problem. So instead of taking into account the degrees of freedom of water molecules explicitly, one approximation is using Brownian dynamic simulations where whatever the interaction with the water molecule is approximated using a random force acting on the particle, right? So this is again an approximation. So the effect of small molecules is incorporated by a noise term in the equations of motion. The equation of motion looks something like this. Again, it is solved numerically at every time step so that we can get the evolution of the particle. Another approach is the Metropolis Monte Carlo simulation. In the morning, we saw some kinetic Monte Carlo schemes. This is very similar to that. Now here, what we do is, instead of solving equations of motion, we sample the distribution using which is obtained from statistical mechanics. Instead of we have something called hops, and these hops are accepted or rejected using the Metropolis-Hastings algorithm, and the properties are computed by averaging over the visited states. It has several advantages over Brownian dynamics because the hops have no relation to reality. Okay, that is an advantage. Now, people also argue, the philosophers also argue that Monte Carlo simulations are not really a simulation because you are not simulating the real process. Because if you are doing molecular dynamics, okay, you are realistically following the equations of motion. You are mimicking something that is happening in the system. But Monte Carlo, it's not really a simulation because you are not following the process. You are just sampling the microstates. Okay. So this can be used for multiple applications. In our group, we are using it to study the formation of the clusters of nanoparticles, right, using simple models. And we can discuss this in detail if you are interested. And you can see the posters of my group outside too. So with this, I will conclude this talk. So what we have seen today is, we have talked about 3 different methods at 3 different scales. At very small scale, density functional theory, right, where electron structure, we wanted to predict electron structure, right, electronic structure. The second thing was atomic scale simulations, where we looked at molecular dynamics and force fields. Third is coarse-grained simulation, right, where we saw Brownian dynamics and Monte Carlo, and we saw what coarse graining is really. So I will conclude my talk here. So I will let Professor Biswas to take the next part, and after both our lectures, like, we will have time for question and answer. Yeah.
Okay, it's a long day, so let's try to just go quickly and keep my presentation brief, just point out some of the interesting features. This was to be presented by another faculty member, he could not come, and some of this has already been covered, so I can go through. So instead of all those details you already heard of nucleation, I'll focus on the latter part, but I'll discuss collisional growth, coagulation, because that hasn't been covered yet. But there are few things to, just one point to take. So we have particles. These are small particles, right? They are in a medium. So one is the move about. So particle transport is a concept we need to understand, okay? And I was just very quickly in the morning mentioning it. You also heard a lot of it, even as we looked at applications and so forth. So one is particles move. They could move by interactions with molecules, Brownian motion, or they could be forces. It could be in a fluid, so they're moving with the fluid, and all of this is important because it's in reactors. What impacts particle transport? It is the size, the shape. You heard a lot about characteristics, how you do measurements, and that's why these are so important. So size, shape, concentration, these are all important parameters which impact transport, okay? Next is dynamics, that particles undergo certain phenomena which change the size of the particle, for example, right? And of course, transport dictates that to some degree. You heard about nucleation, of course, is the birth of particles. There are no particles, and then we create particles. So that is the part which I was going to cover, but I'll go through quickly. But then how do you take all of it and solve the equations? And of course, you should know, why do we even want to do modeling? We want to, our main goal is to make nanomaterials. So let's just keep that, right? I want to run reactors. I want to synthesize and make nanoparticles. Of course, I want to make useful stuff. I want to characterize them. Those are all important. But the models here, we'll focus on that. So these are some fundamental steps. Maybe I'll quickly go through that. So we start with molecules. I'm talking of the bottoms-up approach. We like that because it's a building block. The chemical industry uses it, right? The top-down approach is okay, but we heard of scaling issues. Though when it comes to nanomaterials, I'll be happy to get a very functional material which has applications. So I'm going to use any technique to make it. But we also want to scale up things, and we are talking of large volume production. So we start with molecules. The chemical industry is mature, right? We know how to react things. We can go into a molecular state. We can start with some precursor, produce another molecule, and then create the particle. So that's the emphasis here. It could be multiple species. These molecules cluster and grow, right? Now I'm creating my particle. So that is the nucleation process. But these are multi-component clusters because I might want composite structures and so forth. And after that, okay, each of these has a characteristic time. You heard that from Professor Mukherjee. He was mentioning characteristic times. That is a function of size and of course the time. And I give you some equations. Because I move from a molecular state to a certain clustered state, there is a characteristic time for nucleation. The references are there. We won't go into much detail here, but you can see that there is a certain dependence. The next is collisional growth. Once I form particles, because they move, they will collide and form larger particles if they tend to stick together, or they'll bounce back and so forth. So the collisional growth is one mode of changing the size. The other is what we call condensational growth, because once I have a stable cluster, the molecules can condense on them and cause growth, right? So I always tend to do this. And then I get my multi-component species. So if I look at different times, they are a function of size now, and so forth. And I can, of course, write down expressions. I'm not going to even describe these terms in detail. Please take it as a given. We are running out of time, but they depend on the process parameters, they depend on concentration, they depend on size, and so forth. Okay? So these are some basics. We take all of this, and then ultimately How many? Undergraduate students? Okay, some. How many masters and PhD? Okay, quite a few. So the masters and PhD students have done some fluid mechanics, transport. Of course, if you're a chemical engineer, mechanical engineer, you have done a lot of it, maybe civil engineer, fluid mechanics. So this is the transport term. This is the velocity of the particle, and this changes due to collisional growth and loss of size of particle. This is basically the collisional growth. I left out nucleation. I could have tossed in the nucleation terms, the condensation terms, which we've seen, right? So the dimensionless particle velocity here is given by the fluid velocity. If the particles are in a fluid, it will move. They have inertia, which is due to the drag force. There is a term, this is the diffusion term. We know the Peclet number. Again, chemical engineers will know this. And then the gravity term, and then, of course, external force fields, and so forth. So you look, the equation becomes long, but I want to use this to design my reactors, right? I want to get a certain size distribution at the end. I want a certain composition. I mean, I have to throw in those terms too, but let's see. But let's see, how would I solve that equation? Ideally, I want to know the concentration at every size, right? What is the smallest size? That is my critical size by nucleation, but I'll just say 1 nanometer is my smallest size, okay? It could be 0.5 nanometers, doesn't matter. And a 1 nanometer particle, I'll assume everything to be a nice sphere, has this volume. Just pi by 6 dp cube is the volume of a particle. And what is the next size, next possible size, theoretically? Anyone tell me? I have 1 nanometer as my smallest. What is the next largest size? You don't have to give me a number, or just explain what is it. It's larger than 1 nanometer. By how much? Don't give me a number, just explain. 1 nanometer plus what? Or volume of 1 nanometer particle plus? So what is the next possible size physically? No? Huh? Double the size? You are only assuming collisional growth. What else could happen? You could have a molecule. I'm running a reactor with molecules. So a molecule could come and land on this particle, right? So it's this size plus 1 molecule size. That's why I list the molecular volume here, okay? And I just assume 0.1 nanometers. So it's this plus this is the next size, and keep on adding and so forth. And I want to simulate over 100 nanometers, okay? So diameters are not additive, don't add diameters, but volumes are additive. So at the bottom, I can keep adding them. So let's see, number of discrete sizes. We call this the discrete distribution. I'm accounting for every possible size, right? Because I want to know the concentration at every possible size. This will be my most accurate description. So it's the final volume minus the initial, and each step is the volume of a molecule, right? And what they were saying is 1 nanometer plus 1 nanometer. Yes, that's when 2 particles collide, but the steps is a particle could collide with a molecule and grow. So it is just this by divided by V molecule. 10 to the 8 equations. Which computer on the IIT Gandhinagar campus will solve these? Right? No. Even the most fastest supercomputer, you'll be waiting for a month to solve. And remember that complex looking equation, but I have to solve it for so many different sizes, right? So obviously I need other approaches. and I start again putting everything together, there are these molecular models. I am looking at aerosol dynamic models. I don't want to use discrete because that's too many equations. I can do modal, I can do sectional, I can not predict at every possible size, but in sections. And then I want to couple to reactor models and so forth, okay? And maybe I want to develop theories. So just imagine the complexity, and that's all I want to point out here. You can read all these papers just from even my own group, where we play with these equations and try to simplify it, and from others too. This is not just all of mine. Other people, nice papers in the literature, which will discuss how you solve these and sometimes how you then design reactors with it. Let's talk about machine learning. Everybody wants to use AI and machine learning. How many computer folks here? How many engineers who look for an IT job? Right? This will get you the IT jobs you want at very high salary, if that's what you want. So stay domain specific. If you're a chemical engineer, try to apply IT to chemical engineering problems, or mechanical or civil engineering. And that's what will get you the most money, let me tell you. But let's talk about this. How can I use this to solve those complex equations, right? There are all kinds of neural networks. These are some literature reports again, and I'll of course discuss one of our own in a very simple manner. So let's look at the general dynamic equation only for collisional growth, right? So first I have to train these. We come up with machine learning algorithms. They need to be trained. I can train it by experimental data, or I can run a very accurate model, spend a lot of time, generate the data set, or maybe run it in a sectional mode, and then use this as a training data set, right? And there are certain integral parameters. So I take an initial size distribution, run it for a certain amount of time, get a data set, and look at this. The student generated 60,000 cases, of course, spanning reality, realistic conditions. This was work done in collaboration. You don't work by yourself. So here we actually worked with a professor at IIT Bombay. So the two PhD students cranked out 60,000 solutions and got a good training data set. What do you do next? You take this, and this is the heart of a machine learning algorithm, is you develop a simple matrix multiplier based on this training, right? So I don't want to solve integral differential equations. I do that on the top set, but here we come up with a matrix multiplier. There are weights, there are uncertainties. All of these are built in. Again, I'm giving a very simplistic relationship, and there are a bunch of layers. So by simple matrix multiplication, I can go from my input condition or initial condition to my final condition. This is just to get the multipliers using this training data set, right? So I come up with these matrix multipliers and come up with the sort of layers, multiple layers, which will give me a relationship of input to output. Now, how do I know this is accurate? Of course, it's good for this training set. Then we want to really begin to apply it. We also want to incorporate some physics. I understand the collisional process. In fact, I explained it to you in 5 minutes, right? How the particles collide. So we bring that in terms of the characteristic time, and we do a stepwise simulation, keeping that physics of collisional growth in mind. So this is a hybrid model where we combine some physics with the training and do it in a sequential manner and come up with a much more accurate solution. I'm giving you you have to read the paper to get all the details, and I'm giving a very simplistic description. And then ultimately, you want to compare the predictions of the artificial neural network model with an accurate sectional model. There are other moment models, but you can see they're not as accurate. And this is run for an actual reactor, right? So you see the reactor Ultimately, you also want to throw in experimental data here and see if the predictions are good. Okay, so this is the very simplistic way of describing a machine learning model. You can look at the CPU time. The moment model has the lowest CPU time because it's just an integral model, but the accuracy is not as good. Sectional is the largest, and the hybrid ANN is also lower and realistic. And these are some of the errors that you inculcate as you go through the simulation. So you do this, this works. Now I can use it for other kinds of simulation problems. I will end here. A lot of students over the years, what does our group do? They spend most of their waking up hours understanding this transformation. Once you understand the transformation, you can do all kinds of things. You want to design new instruments. This was mentioned. If you walk into our labs, one of these instruments will cost $100,000. Is that good? I want to know. I set a fire here, right? I want to know what I was being exposed to. I want a sensor clipped on. I'm wearing a watch. It gives my blood pressure, but it doesn't give me the aerosol concentration. So we design novel, low-cost, portable instruments. Of course, there's a startup company now. Students want to make money. That is a high price. They spend about $25 making it, but they can sell it for $350, right? And this is the wearable sensor that one can use. We do computational work, and then, of course, all kinds of applications. This is our driver, aerosol reactors, aerosol CVD systems, new types of photovoltaic materials, energy storage, low carbon fossil fuel use, applications in medicine. I'm most excited about applications in agriculture because this is a high impact area, right? There's someone attending here from an agricultural institute. I think keep going. Nanotechnology has a big role to play. And then ultimately the environment applications to get clean water, clean air, extremely important, right? So with that, I'll pause. We should pause. I think I finished in good time. If there's any questions, we are happy to answer them. Thank you. Yeah. I think there's another session, right? Okay. Okay. Yeah, we can just go to the break. Yeah. Let's save time. Talk over the break. Yeah.
Thank you, Professor Biswas, and thank you, Professor Rane. I can see that a few of you are fighting a valiant battle against gravity. By you, I mean your eyelids are, certainly. So fear not, we have a dose of caffeine for you. Yes, we have a short coffee break. And we have to come back by 5:15. Please ensure that you come back by 5:15.